Stars like our sun colliding probably would not produce gravitational waves which are strong enough to detect. But maybe there are huge black holes, stars that have collapsed and are so dense that a mass the size of our sun would collapse down to the size of Kiev. Be so dense that one teaspoonful of material would weigh billions of tons. If those objects exist in our galaxy or other galaxies and they collided, maybe we could detect gravitational waves. So over a period of 25 or 30 years, people built detectors. And this is the first large gravitational wave detector. It's in the United States, in Hanford, Washington. Identical one in Louisiana. One is in the north and one is in the south of the United States. There are two of them for reasons I'll describe. They're identical. And what they are two tunnels at right angles, each 3 kilometers long. And in principle, if a gravitational wave came down from above, what would happen? This tunnel would get a little bit smaller, and that tunnel would get a little bit bigger. And then this tunnel would get a bit longer, and that one would get a little bit shorter. So in principle, it's really simple. All you have to do is measure the length of this tunnel and to measure the length of that tunnel and watch it change. Easy. Not so easy. Because you can calculate the effect of a gravitational wave from 2 black holes colliding in our galaxy or a nearby galaxy. How big would the effect be? And this is why I'm a theorist and not an experimentalist. Because it turns out you'd have to measure the length of this tunnel, which is 3 kilometers long. You'd have to measure a change in the length as a gravitational wave came by. The length would change by an amount equal to 1/1000th the size of a proton. 1/1000th the size of a proton. Who can do that? We can. Not me. But amazingly, this detector was built to be able to do that. First, it only got to 1/100th the size of a proton. And it was turned on for 10 years and no one saw anything. But then it was improved. And in 2015, I think, it was turned on. And it had the necessary resolution. If these black holes were colliding, this should detect it. Now, there's a lesson here. Because a man named Ray Weiss, who I used to know when I did my PhD at MIT, it's a university in the United States, and Ray was a professor there. And he designed this detector, the first detector. And when you turn on a very complicated machine, you want to tune it up, make sure it's working. So he told his students, okay, we'll just do it, we'll turn it on and we'll see if it's working. Don't take data. Just want to get it working. And the students did something very important, which all students should do. Don't listen to your professors. Man, that's probably okay. They took the data, and 1 hour after it turned on, they saw the signal of gravitational wave signal from 2 black holes colliding in a galaxy 1.3 billion light years away. Now think of that. The signal turned out to last 0.2 of a second, which is the amount of time it took for these black holes to collide. I'll show it to you in a moment. So 0.2 of a second, that signal had been traveling for 1.3 billion years. If they turned on the detector 2 hours later, they wouldn't have seen it. It's amazingly lucky. And as I said this morning to a different group, accidents are incredibly important in science. And the fact that it was there and it just happened to turn on at the right time was amazingly fortunate. Now, how can you measure a difference in length at that small? Well, you use physics, of course. And here is what we use lasers. And you measure basically a distance by measuring the time it takes a light beam to go from one end of the tunnel and bounce off a mirror at the other end of the tunnel. And what we take is a laser beam and split it, and then have it come back. And as the two ends of the tunnel change, you eventually, as you'll see on here, you'll see a wave. But if one of these waves travels a little bit farther than the other, waves will interfere with each other. And if you design it exactly right, so these two waves will negatively interfere, you'll have nothing. You'll have a dark spot on the screen because the peak of one wave will interfere with the trough of another. But if the length changes a little bit, then the interference pattern will change. And you'll see here in a second, you'll see what was a dark spot turn into a light spot. Using this technique of interferometry, you can measure very small time differences and very small length differences. Now, it's much more complicated than that. You actually have to run it back many times. You have to use an incredibly powerful laser. And you have to get rid of lots of backgrounds. Because we're measuring time distances that are very small. So if a truck hits a pothole 20 miles away from that machine, it will produce a bigger effect than this. That's why there are two of them. Because there's lots of noise in each of these detectors, but we have one detector in Washington and one detector in Louisiana. And gravitational waves travel at the speed of light, so you can calculate that it would take about 8 milliseconds, 8 1,000ths of a second, for a gravitational wave to get from one detector to the other if it's traveling in the right way. So all you have to do is look at those two detectors, and there's lots of noise, but you look for a signal that's identical in the detectors separated by 8 1,000ths of a second. And that gets rid of a lot of noise. That's the first thing. So only in 2015 did we have the technology, and by the way, mirrors are vibrating due to quantum mechanical effects by a much bigger effect than we're looking for. So you have to use very complicated new kinds of atomic physics called quantum optics to play with the laws of quantum mechanics, so the motion of the mirror in this direction is reduced, and it uses the highest level technology we now have. 10 years ago it would have been impossible. That's for the experiment, but for the theory we have to calculate what we think a gravitational wave, what effect a gravitational wave would do. That's also very complicated, because two colliding black holes, the mathematics of calculating the gravitational waves is very complicated. Only when we had large supercomputers could we predict a signal. So only in 2015 did we have the theoretical machinery and the experimental machinery. They all came together, and an hour after the detector turned on, here was a signal. This is, you see, half a second. This is a signal in Washington. This was a signal in Louisiana, separated by 8 1,000ths of a second. When you put the two on top of one another, they're identical. And the noisy curve is the data. The other curve is what you'd predict for two black holes colliding. And you see the prediction and the observation agree almost exactly. This is a gold-plated event. You could never ask for an event this beautiful. And it happened right away. It's amazing. Gravitational waves exist. We see them. And you may say, big deal. But the fact that we see them tells us something amazing about the universe. Let me show you a movie. This is just an artist rendering of what it would look like of the two black holes if we could see it. Here are two black holes. We can, comparing the signal to the prediction, it turns out we know that one black hole had a mass of 36 times the mass of the sun, and another black hole had a mass of 29 times the mass of the sun. And the amazing thing is, so we've got two objects that are almost 30 times the mass of the sun, and just before they collide, they're orbiting around each other 200 times per second. It takes us a year to go around the sun. These two objects are moving around each other almost at the speed of light. 200 times a second they're going around, and they produce a signal that has a frequency of 200, and then 300, and then 400 in the audio range. You'd actually hear the signal. And if I had a microphone there, this will actually also play the signal. You can actually hear it. It's in the audio region. But what you see here is space looks a little weird. That's because the black holes are so massive that if we looked at them, if we could actually see them, which we can't, the space would bend around them, and when I make the movie go, you'll see that the stars move. That's because the light is bending around the black holes as it moves. So watch this, it's slowed down. The whole process takes 0.2 of a second. But you'll see what happens, and at the very end, you'll see space jiggle. And that's the gravitational waves. So let's watch it. So this is just the image of gravitational lensing as space is bending around the black holes, if we could see it. And this is very slowed down. These are actually moving around each other 200 times or so. But in the last moment, watch space. It's beginning to jiggle at a frequency. There it was. That was the signal, and it lasted 0.2 of a second, and it caused space on Earth to jiggle a very little bit, but we could measure it. This is a triumph of the human intellect, that we could first know that Einstein could predict that gravitational waves exist, that we could build a detector that could do this, that people would have the courage, the intellectual courage, to spend 30 years of their life building a detector that may see a signal that doesn't exist. Because we didn't know if there were black holes like this we thought there might be, but we didn't know. Greatest triumphs, in my mind, of the human imagination. And we should celebrate that we're alive during this time. Now, maybe the fact that we can detect this doesn't impress you. I hope it does. But if it doesn't, this should impress you. Nature is stranger than we can imagine, in a sense. And I told you that there was one black hole of mass 36 times the mass of the sun and one black hole of mass 29 times the mass of the sun. They combined together to form a black hole. 29. How massive is the black hole that they form? Your students. 36, 29. 36 and 29 come together to form a black hole. What's the mass of the black hole? Who said 65? Who said 65? No one said 65? Wrong! They form a black hole of mass 62 times the mass of the sun. Where did the other three solar masses go? Into gravitational waves. Mass got turned into energy. Now that might not impress you. But our sun will last 10 billion years, burning hydrogen fuel with maybe 1 billion hydrogen bombs going off every second, turning mass into energy. Over the lifetime of our sun, less than about 1/1000th of the mass of the sun, over 10 billion years, will turn from mass to energy. So for 10 billion years, our sun will burn, powering our civilization and everything on Earth. For 10 billion years, and 1/1000th the mass of the sun will be energy. When these two black holes collided, in 0.2 of a second, 3 times the mass of our sun got turned from matter to energy. Meaning that more energy was released in that collision, in that 0.2 of a second, than is released in all the rest of the stars in the visible universe. And we would never have known about it if we didn't have that gravitational wave detector. Now that is amazing. Okay. You don't look enough amazed, so I'm going to show you something else. Since then, we've detected more gravitational waves, not just from colliding black holes, but there are other objects that are very dense. When stars collapse, if they're very massive, after their nuclear fuel burns, they collapse. And if they're very massive, they collapse into a black hole. But if they're not massive, what happens? In a period of about 1 second, the nuclear fuel finishes burning, the core of the star, which starts out to be about the size of the Earth, collapses to the size of Kiev in 1 second. And then it becomes so dense that it basically becomes one giant atomic nucleus of mass number 10 to the 56. At that point, nuclear forces take over, and it can't collapse anymore. So the star collapses, the inside, suddenly it can't collapse. There's a shock wave that goes out and blows out the outer part of the star into what we call a supernova. All the elements that make up your body were produced in stars, because the only elements that were produced in the Big Bang were hydrogen, helium, and a little bit of lithium. But carbon, nitrogen, oxygen, iron, all of that is produced in the core of stars, and the only way it could get into your bodies was if the stars were kind enough to explode, which they did over the last 13 billion years. So that material, you are stardust. You are made of stars. But there was a problem. Everything up to about 100 billion tons in a little teaspoonful of material. And we know there are neutron stars in our galaxy. We can measure them. One can calculate that every now and then, many stars are in binary pairs. And it is still amazing to me that when one star explodes, it doesn't blow the other star away sometimes, and you could have two neutron stars orbiting each other. When those two neutron stars collide, they're very dense, you produce gravitational waves. But unlike black holes, which are just holes in space, there's nothing that comes out. If two neutron stars collide, gravitational waves come out, but so does a lot of other stuff. Gamma rays and X-rays, ultraviolet radiation, visible light, radio waves, all of that comes out from that incredibly dense collision. So what's amazing is, last year, the gravitational wave detector LIGO and another Virgo detected a gravitational wave event that had the signature of two neutron stars colliding. And they sent out an alert to the whole astronomical community. And all the telescopes on Earth, gamma ray telescopes, X-ray telescopes, ultraviolet telescopes, visible light telescopes, radio wave detectors, all looked in that direction to see if they could see the event, to see if our predictions of what would happen when a gravitational wave, when two neutron stars collided, if those predictions were correct. And here's what we saw. This, by the way, is a neutron star. So this is not a real one, but this is New York City here. And you can imagine this is what a neutron star would look like. It'd be the mass of the sun, about the size of New York. And this is a simulation of the event that was detected about a year ago, of two neutron stars colliding. Now, stuff is coming out because these aren't black holes. There's material here. And as they collide, and if I had the sound, you'd hear a little chirp. Now, gamma rays and relativistic jets are emitted. X-rays, as radioactive materials come out and decay, then they turn into ultraviolet radiation. Then the material hits the interstellar medium and produces excitations that's visible light. All of those things are predicted. They were all seen. And this solved a problem that had been around since I was a student. How many of you have something gold right now? Maybe a gold ring or a gold necklace? Anyone? Some people, good. Okay. So you're hesitant to put up your hand. It's okay. So our civilization has been profoundly affected by the desire for gold. It's changed lives. People get killed. People try and win it. People destroyed civilizations. in their desire to get gold. So human culture has been dramatically changed by the presence of gold since antiquity. And I find it incredibly interesting because where does the gold come from? It turns out the ideas we thought we had 30 years ago was that the place that gold is formed is when two neutron stars collide. Because the heavy elements have many more neutrons than they have protons. And where can you get all those neutrons? When two neutron stars collide, there's all this energy, and maybe you can build up the elements after iron. And the idea was a process called the R process and other processes that might produce gold. Well, we were able to observe with the telescopes that we pointed towards the objects that produce these gravitational waves, the X-rays that came from radioactive materials that would be produced in the collision of those neutron stars that would produce gold. And we saw that in the course of a few days, more than 1 Earth mass of gold was created. So when you now look down at your gold ring, that's where it had to come from. One of the most exotic things in the world. When you're holding gold, you're holding the results of the collision of two neutron stars, the densest objects in the universe other than black holes. And we now know that's the case because we can measure gravitational waves from two colliding neutron stars. So maybe gold is valuable, at least from a cosmic sense. We are not just star children, but we are the children of the most exotic, wild events in the universe. Because neutron stars don't collide very often. Very rarely, but the universe is big and old. And that means rare events are happening all the time. Stars explode once every 100 years per galaxy. But there's so many galaxies out there that every second a star is exploding somewhere in the universe. So we can use that if we look out at the universe and try and detect strange things. Now that's where gravitational waves are now. But I want to spend the next few minutes talking about where gravitational waves will be. Because I want to talk about something that's of interest to me, which is another source of gravitational waves. By the way, this is the Milky Way seen at night in a beautiful spot. And somewhere out there were neutron stars that collided and produced material that ended up being in our region of the solar system when our sun began to collapse and the solar system began to collapse around it. It's remarkable that that happens. Still amazes me. Okay. There is another way to look for gravitational waves from a very different source. This is the South Pole. This is a detector that looks at radio waves, not radio waves from stars, but radio waves from the Big Bang. Microwaves, actually. It turns out that there's radiation called the cosmic microwave background radiation that is a remnant of a time when the universe was only 300,000 years old. At that time, matter and radiation the matter was so hot it was 3,000 degrees, that matter and radiation were in equilibrium. But after that time, the matter cooled down, neutral atoms formed, and the neutral atoms were transparent to the radiation, so the radiation could move through. And they saw noise. They didn't know what the noise was. They cleaned out, it was an outdoor telescope, they cleaned it out. It had a white dielectric material, which was pigeon droppings. They cleaned that out, the noise went down, but it was still there, and it bothered them until some physicists down the road at Princeton University told them they had discovered the noise from the Big Bang. And those people who discovered it didn't know what the hell they were doing, won the Nobel Prize. You don't have to know what you're doing to win the Nobel Prize. You just have to do it. Okay? They discovered the afterglow of the Big Bang, the first definitive evidence that the Big Bang really happened. And the Big Bang did really happen. And if you meet anyone who doesn't think that it happens, ask them if they also think the Earth is flat. is dry and high, and so you can, the atmosphere allows the radio waves, the microwaves, to come in a certain region of the frequency band very effectively. So this is at the South Pole. This is a detector called BICEP, and then there's another telescope called the South Pole Telescope there looking at this. It's interesting to me. This is liquid helium, which is delivered. It's cold at the South Pole, in case you wondered, but it's not cold enough. In order to make these detectors work, you have to cool them down to almost absolute zero. And so we have to ship down liquid helium to the South Pole in the summertime. This is the summer. Why? This surprised me when I first learned it. Maybe it won't surprise you, but it really surprised me when I first learned this many years ago. We don't send planes down to the South Pole in the wintertime, because we're worried that if the plane lands, it won't be able to take off again. So that means if you're down in the South Pole and it starts to be winter, you're stuck there for the whole winter. That's why this is one of my favorite pictures. This is this picture from this telescope at sunset. Sunset happens once a year in the South Pole, because in the summer the sun is always above, and in the winter the sun is always below. So this is the moment when it begins to be winter, which means if you take this picture, you're stuck there for 6 months, which is why it was probably taken by a graduate student, because they're the ones we send down there. But this detector, and others like it, may detect gravitational waves from the Big Bang. And I want to talk about that a little bit, and I'll even have an equation, because I felt that there were students and faculty, so I should have at least one equation in this. So here's what we think happened at the beginning of time. The universe is expanding. It's getting bigger and bigger and bigger. And if we go back to a very short time after the Big Bang, a millionth of a billionth of a billionth of a billionth of a second after the Big Bang, we think something very strange happens. For reasons I'll talk about in a moment, we think that the size of the universe increased dramatically in a millionth of a billionth of a billionth of a billionth of a second. The universe increased in size, in volume, by 10 to the 80th. It went from the size of the entire what is now the visible universe today, went from the size of being about the size of an atom to the size of a basketball. Gravitational waves are produced when extreme movement of matter happens. When our whole universe goes burp, that should produce gravitational waves. I want to show you, this is the equation part, so some of you can see now, and then in a second you can wake up. There's a miracle. It's not really a miracle, but there's something amazing. Right now, maybe some of you who work in physics departments are working on the development of quantum materials like quantum computers, trying to use the weird properties of quantum mechanics and manifest them at human dimensions. Because we tend to think quantum mechanics only operates at small scales. In fact, you are all remnants of quantum mechanics if inflation happened. Because inflation happened because quantum fluctuations become us. But we think what happened during inflation is that there was some field, like an electric field, but a different kind of field, that gets stuck in a certain place and it stores energy. And there's energy throughout space, and the field gets stuck. It's like supercooling water. On a cold day like today, you'll see when cars go on the road, you'll see liquid water. It's because the cars are stirring it up. Even if it's below zero, it'll still be liquid. But the minute the car stops stirring it up, suddenly it freezes, forms black ice. In that moment, when it freezes, it releases energy, because the preferred state it wants to be is ice, and you've been stirring it up and giving energy, and when it freezes, it suddenly releases energy, called a phase transition. We think in the early history of the universe that our universe got stuck like water. It was in a phase that stored energy, and then when that energy was released, all that energy got turned into heat and particles, and the hot Big Bang happened. But during this time when that energy was stored, that's when space suddenly expanded very fast. Now, how do we know when the transition happens? If the universe is staying there, if there weren't for quantum mechanics, it could stay there forever. The phase transition might never happen. But quantum mechanics tells us that things are fluctuating all the time. And quantum fields fluctuate all the time, and I'm not going to go into this much, but they change. This field is wiggling back and forth, depending upon the expansion rate of the universe, it turns out. And if it's wiggling back and forth in one place in the universe, it can wiggle so far that it falls over the edge, it releases its energy. So here, inflation ends a little bit before here. But if inflation ends a little bit here before there, it turns out the density here is a little bit lower than it is here. The energy that's released is more here than there, because this happened later than that. And that means you have small fluctuations in matter and energy. But those small fluctuations in matter and energy, if you produce a little more matter here than there, it's denser here and there, that collapses to form a star, and planets, and people. We would not exist if it weren't for those quantum fluctuations. You are quantum fluctuations. You're remnants of quantum fluctuations, if this is true. It's something we don't talk about enough, but it's an amazing, remarkable miracle, and we can calculate how much it is, it doesn't matter. But it really means that if this is true, then all of the stars and galaxies and planets and aliens and people and everything came from quantum mechanics in the earliest moments of the Big Bang. But gravity, we think, is also quantum mechanical. And if there are fluctuations in other fields, there'll be fluctuations in gravity in the early universe during inflation, and those fluctuations during inflation will get frozen in as gravitational waves after inflation ends. So the picture of the universe that we have, if this is right, and this is hard to read, but it was from a Scientific American article I wrote a long time ago, and I spent a lot of time with the artist, so you have to look at it. But we think there was the Big Bang, then inflation happened, and the universe suddenly blew up, and then it started getting bigger and bigger, and this is the time of the cosmic microwave background. And what happens? It produced gravitational waves of all frequencies. A period, 1 second, 10 seconds, a century, 1,000 years, 1,000,000 years. What happens? Well, let's say you have a gravitational wave that has a period of 1 second. But the universe is 1/10 of a second old. Well, the gravitational wave doesn't start to vibrate yet. Space doesn't start to vibrate because there's not enough time for it to start to vibrate. But when the universe becomes 1 second old, the gravitational wave starts to vibrate, space starts to vibrate, and then that gets big. It's not just that we're able to do that, but it turns out, because inflation predicts that the universe gets much, much bigger, more quickly, our visible universe could just be a small part of what we now call a multiverse. And it could be that one region ends inflation now, creating the universe we see, but there could be other regions far away which are still inflating and haven't yet ended inflation. And there could be many, many different universes. And in each universe, the laws of physics could be different once you leave inflation. This idea called a multiverse, lots of theorists are thinking about it, but it sounds like religion or philosophy, not science. Because who could measure other universes? We'll never be able to measure them directly, but if we could measure gravitational waves from inflation, we could see if inflation happened, and we can infer indirectly that there are other universes. We can infer indirectly that maybe there are other universes, and in our universe there are galaxies, and other universes there may not be. You can turn metaphysics into physics. And any time you can turn metaphysics into physics, it's a success. Because metaphysics is just talk. Physics is real. On the scale of things, religion is down here. And metaphysics is here, and physics is here. And any time you can go in that direction, it's a good thing. So we are on the threshold in your lifetime, maybe, of being able to detect a signal from the Big Bang and maybe begin to learn about the origin of our universe. That's the astronomy and physics of the 21st and 22nd centuries, and you will be able to participate in it. And so I think When we look at this night sky, as I say, it inspires me. I hope it inspires you. But it's just the tip of a cosmic iceberg. What we can see is far from all that there really is. Earlier today I talked about dark matter, but the universe is full of things. There's far more in heaven and earth than are dreamt of in our imagination. And if we keep looking,